Okay. So in the last class, we were discussing about ensemble classification, right? So especially we had discussed about, like, suppose we have a data set, then instead of building one single classification algorithm or one single classifier on it, we can actually build multiple classifiers, and then like let each on any test data point, we can let the different classifiers make their prediction. Then we will take some kind of a vote over their predictions and choose the final level accordingly. So, and for this purpose, we had also decided that the votes will not be equal of all the classifiers, but rather we will have some estimate of the efficiency of the different classifiers, and the votes will be weighted according to that efficiency. And so, so from where will these multiple classifiers come from? So we had decided that, like we had discussed, that it can happen in uh, three different ways. So one is that we can have on the same training set, we can use different classifier functions. The other can be that we split the data set into multiple parts and train a classifier on each part of them. Now those classifiers may be different or the same. That is, it's possible that in each of the different classifiers we like train one decision tree for each, or one neural network for each. It can also happen, though it usually does not happen, that on one part we train a neural network, on another part we train a decision tree and things like that. And what can even another possibility is that we can select different subsets of the features and train a classifier for each of those subsets. So what like if this thing happens, and if the classifier that we are training on each subset of the features, then this whole thing is known as the ensemble of these classifiers, or is becomes known as the random forest, which we had seen, or we had discussed, is one of the most like successful classifiers in various real world problems that we have come across in recent times. So of course we cannot, like we have earlier also said, that no classifier is inherently better than other classifiers. Given any two classifiers, you can always come up with some specific data set or some specific set of features on which any one of them works better than the other. So in fact, there is like there are two things, or two theorems related to these matters with rather interesting names. One is the no free lunch theorem. The other is the ugly duckling theorem. So these two theorems we may briefly talk about in tomorrow's class. So both of these are basically related to, like, it is in general we cannot say that one algorithm is better than the other, or one set of features is better than the others, or anything like that. But the formal statements of these theorems we may see in the next class. But this is theory. But practically speaking, on like when we are dealing with large data sets, as we do nowadays in various real world scenarios, say, related to, say, in various domains of technology, business, etc., or other problems. Like some of the, as most of you may have heard already, that say on image classification kind of tasks, neural networks are shown to be extremely successful in various other tasks also, which is why most of the tasks, or like which are performed, let us say related to natural language processing and so on, we see are being done with the help of neural networks. But neural networks again require a lot of data and computational power for training. So another algorithm which sometimes comes close to neural networks performance without requiring so much of data or computational power are random forest. So so these on like the basic thing here is that the ensemble idea is a very strong idea, and it often, and though it cannot be proved theoretically, but at least in in many practical situations it works better than expected. Now, today we will discuss about another type of ensemble methods. This one is called boosting. So in the last class, we were talking about taking an ensemble of classifiers and then using different weights on each of the classifiers. That is, the different classifiers will vote and their votes will have different weights. Now, in case of boosting, what we will do is, in addition to giving weightage to classifiers, we will also give weightage to examples. That is the training examples when we are training the classifier. So like you may remember, like when we are talking about the bootstrap aggregation or the random forest, we had mentioned that some data, no, I mean not random forest. When we are talking about the bootstrap aggregation, we had mentioned that some of the data points are going to be chosen multiple times. It's like when the data sets were being replicated. So we said that each version of the data set will be a version of will be some kind of a distortion of the original data set, in which some of the examples will not occur and some of the other examples may occur multiple times. Like in this case, we saw x1 is appearing twice. In this case, x3 is appearing thrice and things like that, but some are not occurring. So then what exactly does it mean for a single data point to appear multiple times in a training set? So we had discussed that also in the last class. So does anyone remember what is the significance of the same data point appearing multiple times? Yes, we had discussed in the last class.
Weight of that training sample would increase, sir.
Yes, the weight of the training sample will increase. If the same training sample is to be used 3 times, that means if a mistake is made on that training sample, then it will be equivalent to 3 mistakes. And we know that when the classifier is being trained, what it tries to do is to minimize some kind of a loss function. And if it makes many mistakes, then of course the loss function will increase. So those points which have high weightage, we try to that the I mean the classifier will try to adjust itself so that it does not misclassify or does not make a mistake on those heavyweight points, because if they do so, then that will be equivalent to like a large increase of the loss function. So that is why we had talked about this weighted training, and like we had also shown you or discussed like how we can have weighted nearest neighbor or weighted decision tree classifiers also. So the boosting is based on the same idea. So what happens in case of boosting is that, so we make some prediction initially. We have an initial classifier which can be a weak classifier, that is just better than the random classifier. Now, what happens after that is the weak classifier will of course make lots of mistakes, or several of the data points it will predict the wrong label. Now, what we will do is that we will identify those data points where the error is high. That is, which in case of classification, that means which have been misclassified, and in case of regression, it means whatever error or mean square or whatever we are calculating, that error is high. So then what we will do is that those examples on which the error is high, or on which the original classifier made some mistake, we will increase the weights of those examples, and the weights of the other examples will be decreased accordingly. So now what will happen? Now, because examples on which some mistake was made initially, so when their weight increases, that means now if we again train a classifier, it is unlikely to make mistakes on those points. But the weights of the other data points have decreased, so they are now free to make mistakes on those points. And the whole thing will just keep on repeating. So there will be multiple rounds or multiple iterations. In each iteration, we will find out which all points a mistake has been made, and accordingly we will increase the weights of those points or those examples, so that the next classifier which comes in will not make mistakes on those points. And we will see that if we just keep on doing go on doing this, and finally we will get an ensemble of classifiers which have been trained on the same data points but with different weightage. And then we will find that when we take the uh, that is ensemble prediction by these classifiers through the way of voting, we will find that we are getting much higher accuracy than the initial classifiers. Okay, so let us understand this matter with an example. So let us say that these are the few points, the points which we need to classify. So as you can see, there are five plus points and five minus points. Okay, so here 5 plus and 5 minus points are there. Now suppose this is my classifier, this line which I have drawn here, so it's a two-dimensional feature space. So this way it's like, let us say the first feature x1 is along the x-axis and the second feature x2 is along the y-axis. Now what I am doing is, we are just drawing a line like this. That is, everything on one side of it, or everything on the right side of this line will get label red. That is to say, they will be considered as minus, and everything on this side, all points will be blue. That is, they will be classified as plus. Okay. So red and plus basically means blue and red means minus. Okay. So by the way, so what kind of a classifier do you think this is? The one which like, if I say that like this line, like everything on the right side of this line will be called as will be classified as minus, and everything on the left of this line is going to be classified as plus. So what kind of classifier can this be?
Binary plus.
Decision tree.
Binary, fine, but I mean, what type of classifier? Could it be a neural network, k-nearest neighbor, or what?
Decision tree.
Decision tree, right? So exactly, so the criteria can be that if x1 greater than some, let's say some value small x here, predict red, else predict blue, correct? So this is a decision tree classifier. So now let us see what it has done. The two blue, like these two blue points have been correctly classified, and these 5 red points have also been correctly classified, but these 3 blue points have been classified as red. Right. So here what is so here we can see that there is a 70% accuracy. 10 of the 7, I mean 7 of the 10 have been correctly classified, while these 3 are misclassified, right? Now, so now what we will do is, as discussed earlier, we will somehow increase the weights of these things, of these examples. So here I am denoting these by large plus, indicating that their weight has increased, while the weights of the others have proportionately decreased. So what we will like that is because the weights are like a relative thing. If I increase the weights of everything, then it is basically same as not weighting the increasing the weight of everything. So the weights have to be relative. So what is typically done is that the weights of all the examples, the total weight of all the examples are conserved, so that when the weights of a few examples are increased, the weights of the others must be proportionately decreased. Okay. Now, so these have been, the weights of these have been increased, the weights of the others have been decreased. So now whichever or whichever model I am choosing, it will pay a heavy penalty if it misclassifies these points, right? So the penalty which it initially paid, let us say, is 3. Okay. Like why 3 is like, let us say all of them initially have weight 1. So first stage, like let's write down uh, the weights are equal to okay, let us say 1/10 for all of them. So in this case, the 3 mistakes have happened. So the total penalty we paid is 3/10. Now what I am going to do is I am going to increase the weights of these points, so that let us say they are misclassified points. Their weights become 1/5 instead of 1/10. Okay, so there are a total 3 of them, so their total weight becomes 3/5, and so the remaining weight is 2/5, which is to be divided into among all the other 7. So you can see that the other points, each of them have weight only 2/35. Correct. So like one is like these points, they have now weight 1/5, and the other points have weight only 2/35. So, like I'm not saying that the weights has from 1/10 it must go up to 1/5, but so this is just an example to give a basic idea of what is happening. So now if this classifier is to be chosen once again, now the penalty becomes equal to 3/5. So what was initially 3/10 has now become 3/5. So clearly this is not acceptable. So this is a large increase of the penalty. So we will try to build a different kind of classifier which will try to make sure that the penalty paid is less. So let us say I choose this classifier. So this is again a decision tree, but with a different threshold. So like here the criteria may be something like x1 greater than some, let's call this as small x2, or let us call it as, say, okay, something else. Let me call this as a1, let me call this as a2. Okay, so if x1 is greater than a2, then red, else b, blue. Fine. So now we are saying that all these 3 points with a high weightage, they have now been correctly classified. They are all classified as blue. These 2 points are now classified as red, but now these 3 points have been classified as also been classified as blue. These red points have been classified as blue. So totally there are still 3 mistakes. So the accuracy of the classifier is still 7/10. I mean, this one had almost also 70% accuracy. This is also having 70% accuracy. So that way there has been no change. But the points it had initially misclassified, now it is correctly classifying them. But these points it's now misclassifying. So what is the penalty paid? So this classifier, what is the penalty it is paying? So we have already seen that this classifier paid the penalty of 3/10. Right? Now, what is the penalty being paid by this classifier?
6/35.
Right. So these 3 are being wrongly classified. Each of them we have already seen they have a weightage of 2/35. So that 2/35 into 3 is 6/35. Good. Okay. So now what we do now like so now these 3 points have been misclassified. So now I want to increase their weightage so that they are now correctly classified. So the on the other hand, these points have now been correctly classified. So I can bring down their costs. So what I will do is that they are current for right now for each of these their weights are 2 by 35. So from 2 by 35, let us say I increase their weight to what to say, maybe 1 by 7. Okay. So each of them has weightage 1 by 7. So that means their total weightage is now 3 by 7. The remaining weightage 4 by 7 is to be equally divided among all the remaining 7 points. So each of them will have 4 by 49. Okay, so now, these misclassified points, they now become big like this because their weight has increased to 1/7, while the others, like they have become small, their weights are only 4 by 49. Now what is done is that, so now the classifier has to be chosen in such a way that these 3 points are correctly classified. And it turns out that the classifier we get now is, let us say, like this. So now the criteria is something like, if x2 is greater than a3, then predict blue, else predict red. Correct? So now we see that so as you can now see that these uh, so which points are now wrongly classified? This one is wrongly classified, red classified as blue, and these two blues are classified as red. Okay, so now we can, but the accuracy still remains 7 by 10. As you can see, in all the 3 cases, the accuracy remains 7 by 10. Because the accuracy is like it's the neutral accuracy, not taking into account all these weights and so on. Okay, so but if you see what is the penalty, so what happens to the penalty, so we can now understand that like each of those the points which have now been misclassified, each of them had weightage of 4 by 49. So 3 of them, so now the penalty has become that into 3, that is 12 by 49. Correct. And then like if I want, I can continue this also, but let us for now, let us say that I will stop here. That is, I have now got 3 different classifiers. I am now simply going to take a vote of all of them. Okay. So so now I have to take a vote of these 3 classifiers for each of these data points. And if you take the vote, then let us see what is happening. So first of all, when we are taking the vote, we can see that all of them should have or may be given equal weightage, these 3, because their accuracy is 7 by 10. This accuracy is, of course, the accuracy on the training set itself, and when we compute the accuracies, I mean the weightage of different classifiers, we do it not on the training set but on some common validation set. But if we assume the distribution of that common validation set to be the same as the training set, so we can assume without a too much of, like, without a loss of generality, that all of them will have the same weightage on that common training set, which is roughly equal to 70%. There is no great difference between the 3 classifiers. So we can say that all 3 of them have equal weightage. So we'll just go for the normal voting. So what happens? So let us consider this point, right? So this point was classified as red in this case, blue in this case, and blue in this case. So we will classify it as blue. Similarly with these points, all these points have the same fate. They are all classified as blue twice and red once, so they are blue. If you consider this point, then this is classified as red twice and blue once. So I will classify it as red. And this point is always classified red. So it will continue to be classified red. these points, like they are classified as blue twice and red once, so they are blue and so on and so forth. Okay, so this way you will find that after taking the vote, what is happening is that all the red points have been classified as red, all the blue points have been classified as blue. So now the accuracy is 100%, right? So each of these initial classifiers, they had 70% accuracy, but when you are taking their vote, it becomes 100% accuracy. So that is the strength of this idea of boosting or the ensemble classification. So, however, this has certain what I just told, the example which I just told you has a degree of arbitrariness about how to increase the weights of the different examples. I mean, what has like the basic idea is that when I increase the weights of an example, then it should I mean, the next classifier which is being chosen, the weight increase should be significant enough so that the new classifier is forced to classify them correctly. I mean, say suppose from 1/10, suppose I increase their weight to say 1/9. Okay, it's possible that if I used the same classifier, then its weightage would be just 3 into 1/8, which is like 1/3. So it's possible that it will like if I choose another classifier, it may just continue to have the to choose or to classify like this only rather than in any other way. So the weight changes should be significant enough so that the next classifier is forced to change to classify these points correctly. At the same time, they should not be so high that the classifier will focus entirely on correctly predicting these points while not giving any thought to the remaining points. So like in that case, what will happen is basically that it will overfit on these points. It may do something ridiculous like this, that only these points are to be predicted as blue, everything else may get predicted as red, which is also a bad thing, right? So I cannot increase the weights of these points too much, nor do I want to raise them too little. So in general, it cannot be mathematically proved that what is the optimal degree by which these weights have to be increased. But there is an algorithm which is, as usual, a heuristic, that is the Adaboost algorithm. So what is the Adaboost algorithm saying? So it initializes the weights of each training sample to be just equal, be 1 by n, just like we had taken 1/10 in the example. Now what it is saying, so there will be a certain like the fixed number of iterations. In each iteration, a new classifier will be learned. So just like in this case, we had 3 iterations, so 3 classifiers will be learned. So the same thing here also. So what is happening? Learn a classifier on the training examples according to the weights W. Correct? Learn a classifier any classifier. So this one, let us say, is the classifier H1. So according to the weights W means the yesterday we have I mean in the last week's class we had already discussed what is weighted nearest neighbor, weighted decision tree, etc. So whatever you are using, let us say decision tree. So you will take into account those weights while while building the classifier. So once the classifier has been built, what you do is you calculate the weighted error like this. And so this is weighted error. Like in case of classification problem, the weighted error is just I mean the loss function is just the 0, 1 loss function. I mean, if the predicted level, if this is the predicted level and this is the true level, if these two match, then the error is 0. If they do not match, then the error is 1. If it is a regression problem, of course, it will be something else. So instead of writing indicator function, let me just write it as a general loss function. Okay, and each of these errors are to be multiplied by the corresponding weightage. So this is the weighted error. Now, based on the weighted error, I said like this weighted error is to be calculated like either you can calculate it on the training sample itself or on a common validation set. I mean, ideally it should be done on a like a common validation set, though for shortcut we will do it on the training set itself. Okay, so once this thing is done, then what we will do is we will set the weight of the weightage of the classifier like this. Okay, so yeah, so once again the weightage of the classifier can be set either according to the weighted error or according to the actual error itself. I mean the unweighted error. Like here the weighted error was things like 3 by 10, 6 by 35, 12 by 49. This the unweighted errors were 3 by 10 in all the cases. So like you can choose like either this or the unweighted error. So there are like multiple versions of the Adaboost algorithm which set the classifier's weight in different ways. Right. So once I have set the this weightage of the classifier, then what I do is I update the weights of each training example. So those examples which were wrongly classified, their weights are increased are like multiplied by this quantity like e to the power 80 where 80 is this thing, right? And those which were correctly classified, their weights are multiplied by e to the power minus 80. So you can just convince yourself that if 80 is, I mean, if they you can convince yourself that uh, in multiplying by this increases their weights and multiplying by this decreases their weights. The weights will never become negative because we are taking e to the power this thing, but like it can be like either greater than 1 or less than 1. If it is greater than 1, then it will increase, of course, and if it is less than 1, then it will decrease. And so after that, all the weights are normalized so that they continue to add up to 1. So this is the reason for doing it is, as I said, that these weightages, these are relative. There is there is no you may say that why that is while it is important to increase the weights of the points that are correctly classified, but why decrease the weights of the points? I mean, while it is important to increase the weights of the points which are wrongly classified, why decrease the weights of the points that are correctly classified? You can keep their weightage as common constant while increasing the weightage of the the misclassified ones, right? So that you can say, but the thing is that, as I said earlier, uh, in like weight is a relative thing. You cannot like have the best of both worlds in this case. Like if you have to increase the weights on something, the exercise does not mean anything unless you decrease the weights of the others. Okay, and in any case, you we have to do this normalization thing. So basically after this we just keep repeating this set of steps. Like at every stage we learn a classifier like according to the weights. So we have already discussed what is meant by a weighted classifier. Whatever classifier we have got will have some kind of a weighted error which we will calculate either on the training set itself or I mean, you often done on the training set itself, but ideally on a separate validation set. And according to that error, the weightage of that classifier will also be set like this. Next, we will come back to the training set, uh, check each training example, see whether it is being correctly it's predicted or not. If not, then its weight will be increased, else its weight will be decreased. And then we will go back in training a new classifier, right? So finally, what happens is that we will get a collection of these classifiers which we are denoting as these H1, H2, etc., along with their weights A1, A2, etc. Right? So the points the weightage which we give to the different points, that is for internal purposes of the algorithm, but finally they are not those point weights are not to be not for any further use. The whole thing ends there. So what we get effectively is a set of classifiers which also have their weights. And then of course on the test set we can like use these classifiers in the usual way to so that they can do the weighted voting. Okay, so this is the Adaboost algorithm which makes use of this idea of boosting. So boosting is basically just to remind, boosting is the idea of like identifying the examples on which mistakes are being made and then increase the weights accordingly. Okay. So this is one boosting algorithm which we studied today. There are other boosting algorithms also which we will discuss tomorrow, like the gradient boosting. But before that, let's also discuss a few simple ideas based on this ensemble. So one is the like mixture of experts. So it in some situations it might happen that like suppose you have a large number of data points which you want to classify. Now it may happen that a single feature may not be sorry, a single classifier may not work in all the cases or in all situations. Like as you can try to see in this example, suppose this is one classifier which is like this line. So you can again understand that like just like these line or line based classifiers you can interpret as a decision tree. Similarly in this case also you can consider these to be decision trees. So so you or rather decision stumps to be more precise, because it's like only one feature. So so this classifier, what it is saying is that everything on this side of the line will be classified as blue, everything on this side will be classified as red. So till this point, as you can see, that is fair enough. But at this point, from this point onwards, you see that many of the blue points also start appearing on the red side. So if I can like continue classifying using this classifier in these parts of the feature space also, then I will be getting into trouble, because here like these blue points will get misclassified. Correct? So another possibility is this classifier. So so this is saying everything on this side is to be classified as red, everything on this side as blue. So till this point that was fine, but if I continued like this, then we will see that all these blue points I will end up classifying as red, which is a problem. Right? So this classifier is also not a good idea. So, but as you can understand that the whole feature space can be divided into two parts or two halves. In one half, the first classifier is useful. In the second half, the second classifier is useful. So, like there has to be some kind of a gate. On one side, we will use one classifier. On the other side, it's another classifier. So this is different from the usual ensemble classification. So it's in the sense that there are multiple classifiers, but at for any given point, only one of those classifiers is to be used. It's not that we will use both classifiers and take a vote on them, but it's like both classifiers will, or there can be more classifiers like this also. The whole feature space will have to be divided into different regions, and in each region we will have one different classifiers. So this is the mixture of experts system. Okay. Now another interesting thing way in which we do utilize this idea of ensemble classification is when we are doing multi-class classification. Okay, so so most of the problems which we have considered so far are binary classification. I mean, not always, but like say for neural networks, when you are using the softmax functions, or for there is naive Bayes classifiers also, we considered multiple classes, but in general, the most fundamental kind of classification is the binary classification. And especially in case of decision tree, or like after this, when we come to linear classifiers, we will see that is like the most natural way of classifying in the like in case of decision tree. Of course, a tree can be any, like any RE tree, like we can have this kind of tree also. This is also a possible tree, but the most fundamental kind of tree, or the best known tree, is the binary tree, where every node has two children, right? So these kinds of things will work best, like in case of binary classification problems. So one way in which we can use binary classification to also do multi-class classification is, like, can be done in two ways. One is one versus one, the other is one versus all. So in case of one versus one classification, so what we basically do is, like let us say there are k classes. Okay. So what we will do is, like we will build multiple classifiers, but at every stage I will choose any two of them. So as you can see here, there are three different levels: the circles, the squares, and the triangles. So what I will do is I will choose any two of them. Let us say the circles and the squares. So the triangle points, I, for the time being, I neglect. I assume that, I imagine that they are not there. So that is, I focus only on these two sets of points, and I build a classifier which can separate them. So like you can understand this is some kind of a decision tree. Like it's like you can say that there is some kind of it's something like this. Okay, it's not, maybe it's not fair to, okay, let's not call it as a decision tree. It's actually a linear classifier. So basically the idea being followed here is that greater than some b, then you classify circle, and if it is less than b, then you classify it to be square. Fine. So this is the this is the classifier. This is the and the other thing is then let us say take two other classes, another pair of classes. Let us ignore the circles and let us focus on only on the squares and the triangles. So so like this, in that case, this is the classifier. Then again we ignore the squares and consider the circles and the triangles. So for them, this is the classifier, right? So basically now we have got three classifiers, one like this, one like this, and one like this. Now what we will do is, so now suppose a new point comes. Suppose that that point is here. Okay. So now what I will do is that I will classify this point with respect to all the classifiers. So if you consider this classifier, this is between circles and squares. So let us take a vote: circle, square, and triangle. So in this case, like as you can see, the point is here. So it is on the side of the squares. So I will classify this point to be a square. Now comes this exam case, this classifier. So here it is still on the side of the squares. So I will classify it as a square. And in this case, the point is here. So it's like now it is on the side of the circles. So I still now this time I classify it as a circle. Okay, so now you can understand that there are two classifiers have called it as a square, and one classifier has called it as a circle. So it's like this point will be classified as a square. Right. So this is the idea of one versus one classification. Another idea, similar idea, is the one versus all classification. Okay, by the way, so in this case, so how many classifiers do I have to make like this?
NC2.
C2.
Not NC2, but KC2. N is the number of points, K is the number of classes. So it's K choose 2. At every like in every case, I am choosing any two of the classes. The number of points is like whichever whatever is the number of points belonging to those classes we'll use. But but in each classifier will use or will focus on only two of these k classes while pretending that the points in the other class do not even exist. So okay, so two total KC2 classifiers. Other possibility is one versus one classification. So what is that? This idea is now like at every stage. So let us say that there are four classes. So, or let's say in this case also there are three classes. So what you do is that when you are doing like you focus on in the first round, you focus on only one class. Let us say the these cross classes. Okay. So now what you are going to do is you will consider all the points in all the cross points as class 1 and all the non-cross points as class 2. That is these triangle points, the square points, you will just imagine them to belong to the same class called non-cross. So it's like you will reduce it to a binary classification problem. And then accordingly, let us say you get some a classifier like this. Like it's again another some kind of a linear classifier. So it's like saying AX1 plus BX2 plus C greater than 0. We will call as you'll predict their class to be cross. If it is less than 0, then you predict their class to be not cross. Okay, so this bar just means the complement of cross, means not cross, anything other than cross. Similarly, you like when we come to the then we focus on the green class, then we again divide the points into two categories, the greens and the non-greens. So everything on this side will be classified as green, everything on this side will be classified as a non-green. Similarly, blue and non-blue. So now we have got an ensemble of three or k different classifiers. Right, and now we like when a new point comes, I have to take a again I have to take a vote among them. So so let us say cross, uh, triangle and square. Let us say the new point that we are focusing on is here. Okay, so what happens when we consider this this cross versus non-cross classifier? It gets classified as a cross. Right, next the triangle versus non-triangle classifiers, it gets classified as a triangle. And the circle sorry, the square versus non-square classifier, it gets classified as non-square. So none of these. Okay, so now we are in a bit of a dilemma. We have got like one cross and one triangle. So obviously now we have to consider the weights of the different classifiers on a validation set and things like that. Okay, so, like we can actually like if it is like if the point is somewhere here, then it will become even more complicated. Like this class like with the red classifier, the cross versus non-cross classifier, will call it as non-cross. This point will call it as non-triangle, and this classifier will call it as a non-square. So none of the classes will get any votes. So this is one region where it will be classified as none of these, or I cannot decide, cannot be decided. So like this one like in case of these one versus all classifier, there is a region like there are regions like this where we may not be able to assign any label to the data points. But still the advantage of one versus all classification is that in this case there are k classifiers required, while in the previous case KC2 were required. So the number of classifiers required in this case is less, but their classification power might be accordingly less also. In this case, the number of classifier is more, but the classifying power or the discriminative power is again also more. Okay, so that's about these like today we discussed about the Adaboost algorithm. Tomorrow in tomorrow's class we will start with like one another form of boosting which is known as the gradient boosting. Okay, so we will discuss that in tomorrow's class. Yeah. So I'm ending today's class a little bit ahead of time. And by the way, has Jiaul sir already informed you about the test?
No, sir.
Okay, so I will inform you tomorrow. The